welcome to tonight's presentation hosted by the Washington, D.C. chapter of the American Scientific Affiliation. My name is Mike Beidler, president of the D.C. chapter. I'm an ASA fellow and I serve as a member of the ASA Executive Council. I'm a retired naval officer and I currently serve as head of operations for the Undersecretary of Defense for Research and Engineering's Joint Capability Technology Demonstration Program. That's a mouthful, but what that is we manage a sizable portfolio of rapid prototyping projects that use mature technologies to create innovative solutions for current and future problems that U.S. and allied militaries face. And with me tonight is ASA fellow Cy Gart. He serves as both the DC chapter vice president, and he's also co-editor of the ASA's online magazine, God and Nature. And Cy, I'll give you a chance to introduce yourself.
Hi, welcome everyone. What I'll mostly talk about is the magazine that Mike mentioned, God and Nature. It's a not peer-reviewed. It's a magazine that comes out quarterly, online only, and we accept essays, poetry, stories, artwork. It's basically a magazine format online, and the only rule is that everything has to relate to some form of science and Christian faith. So anyone who has something they would like to think about submitting, you can look for the magazine on the ASA website, which you see on that slide at asa3.org. And if you look at publications, you'll find God and Nature. Take a look at it and you'll see guides for authors, and you can look at some sample material that's there. And we're happy to accept material, as I said, on any subject. It doesn't matter if you're a member of ASA or a PhD scientist, as long as you have some expertise in the field you're writing about.
We're pleased to have as our guest speaker tonight, Dr. Fazale Rana. He is a biochemist. He's the president, CEO, and senior scholar of Reasons to Believe. That's an organization dedicated to communicating the powerful scientific case for God's existence and the Bible's reliability to both Christians and non-Christians. And Fuzz may go into this a little bit later, but he converted to Christianity during graduate school. And though he initially embraced the evolutionary paradigm, he eventually drew the conclusion that only a creator's involvement could explain the elegance of biochemical systems. And so after a pastor challenged him to read the Bible, he became convinced of the validity of Christ's claims and of his own need for a savior. He's got a BS in chemistry with highest honors from West Virginia State College and a PhD in chemistry with an emphasis in biochemistry from Ohio University. He also completed postdoctoral work at the universities of Virginia and Georgia. And before joining RTB in 1999, he worked for 7 years at Procter & Gamble as a senior R&D scientist. And to date, Fuzz has addressed more than 500 university, church, and conference audiences across the country and abroad. He also has a number of books, and I'm going to put some titles and some links in the chat box for everyone there. And a couple of these books is Humans 2.0, Scientific, Philosophical, and Theological Perspectives on Transhumanism. The Cell's Design, How Chemistry Reveals the Creator's Artistry. And then the book upon which Fuzz's presentation tonight is based, that's Fit for a Purpose. Does the Anthropic Principle include biochemistry? I just finished reading it this week, and it is excellent. I particularly loved discovering that Fuzz has a love for music, and he and I have extremely similar, if not identical, tastes. So it is a real treat to be able to read about his favorite musical artists. He starts every chapter with talking about some of his favorite musicians and bands and how those particular musical styles or lyrics have some sort of analogy in biochemistry. So it is a very entertaining book as well as educational. So without further ado, I'm going to turn the discussion and the screen over to Fuzz. So thank you for joining us tonight, Fuzz.
Well, Mike and Cy, Vicky, thanks for having me. I very much appreciate the opportunity to be here with you tonight. Thanks again. And what we're going to be talking about is this question, does the anthropic principle extend into the realm of biochemistry? And, just to get things started tonight, just a fun question, and that would be this. What would you consider to be the most provocative, compelling scientific evidence to think that there is a creator, that God exists? Some people are uncomfortable with making a scientific case for God's existence, but if you're not, what would be the one piece of evidence that you think compels people towards belief in God from science? Just if anybody wants to put it in the chat or yell it out, that's fine. Anybody thoughts?
Well, I've heard atheists say that the most compelling evidence for them that would make them think about it, even Richard Dawkins has said this, is fine-tuning, the fine-tuning argument.
I think another question would be, why is there something from nothing?
Yeah. Well, anybody else? If not, thanks, Cy, for that answer, because in my experience, it's the anthropic principle, or the fine-tuning of the fundamental constants that define the universe, that for many people really represents powerful scientific evidence for a creator's existence. And I've heard similar statements, Cy, from people that are non-theists, that the fine-tuning of the universe really does give them pause for thought. And I think almost everybody here is familiar with the idea of fine-tuning, and again, it's this notion that the fundamental constants, the parameters, the characteristics that are numerical that define the universe assume precise, exacting values. And in some instances, if these constants deviate almost imperceptibly from their value, life simply isn't possible in the universe. And two of the most extreme examples that I'm aware of, at least, would be the ratio of the electromagnetic to the gravitational force constants. If the ratio varies by more than 1 part in 10 to the 40th power, life simply isn't possible in the universe. And this is because the ratio of these force constants impacts star formation. And that in turn has an impact on the types of chemical elements that are possible in the universe. Perhaps the most extreme example would be the fine-tuning of the cosmological constant, which is a constant associated with this mysterious stuff that's dominant in the universe, apparently, the cosmological constant can't vary by more than 1 part in 10 to the 120th power, and life still be possible in the universe. And this impacts the expansion rate of the universe, and that in turn, again, impacts the nature of star formation and the types of chemical elements that would be possible. And this idea of fine-tuning in the universe in and of itself suggests design. If you're looking at fine-tuning, that is kind of an indicator of design. But in addition to that, the anthropic principle is really about the idea that not only does the universe appear to be designed, but it appears to have a fitness for purpose, that it appears to be fit for a purpose, because the constants that define the universe are precisely those constants that you need in order to create a bio-friendly universe where life is actually possible. So it's not so much just the fine-tuning that's critical. It really is fitness for a purpose, and that suggests a teleology to the universe itself, which is why the anthropic principle is so provocative. Now, it's interesting to me that the person that is considered the father of the anthropic principle is Brandon Carter, a physicist from Austria, who, as I understand it, was an atheist. And the story that I've read is that Carter first introduced this idea of the anthropic principle at a conference in the early 70s that was in honor of Copernicus. It was some anniversary associated with Copernicus's life and work, I think a 500th anniversary or something like that. And so there was a symposium where people were presenting papers on the Copernican principle and its implications. And Carter took a contrarian view, where he argued that instead of the Earth being non-privileged, that in fact that we actually live at a just right time in the universe's history and in a just right location. And according to Carter, if we were at any other point in the universe's history or any other location, life simply wouldn't be possible because the certain features of the universe would not be in place that are necessary for life to exist. And he referred to that as the weak anthropic principle. He then also argued that the fundamental constants that make up the universe too must assume precise exacting values, because if they don't, again, life isn't possible. And he referred to this as the strong anthropic principle. And so what Carter did to arrive at these conclusions was a counterfactual analysis that was theoretical in nature, where he held all the constants fixed except for one that he allowed to vary, and then calculated the consequence of varying that particular constant, usually looking at the impact it would have on galaxy or star formation and ultimately the production of chemical elements. Now, the way that Carter interpreted the anthropic principle was in a tautological way, where he argued that, well, of course, we must live at the right location and the right time in the universe, and the universe must have the right physical constants for life to exist, because if it didn't, there wouldn't be observers to recognize that fact. And so that's how Carter, as an atheist, interpreted the anthropic principle. In the 1980s, you have Barrow and Tipler writing this classic work called the Anthropic Cosmological Principle, where they really elaborate on Carter's ideas quite extensively. And in this book, they reinterpret the anthropic principle, where they define the weak anthropic principle as essentially Carter's interpretation, which is, again, this tautological interpretation of the anthropic principle. But they went one step further, and they redefined the strong anthropic principle to argue that the universe is some type of imperative. And what they meant by that is that something is dictating the universe to take on the character that it assumes, so that life is possible. Either the universe is fine-tuned because of the multiverse concept, and that we are in the lucky universe that has the just right constants for life to exist, or that there is some kind of intelligent agent, an agent that is responsible for producing a universe so that life is possible in the universe. And what's interesting is with this proposal and this particular interpretation of the anthropic principle, they introduce teleology into cosmology, into astronomy and astrophysics. Now, in a sense, when it comes to the anthropic principle, you really have two possible interpretations. One is theistic and one is non-theistic. And of course, everybody, I think, accepts the weak anthropic principle as defined by Barrow and Tipler. The question is, how do we understand the anthropic principle? Which version of the strong anthropic principle is the appropriate one? Is it just simply the outworking of a multiverse, or is it due to an agent that intentionally has designed the universe to be in this particular way? And I submit to you that one way you could make a case or strengthen the case for theism would be if you see anthropic coincidences manifested not only in the laws of physics and the constants of physics, but if you also see it manifested in chemical phenomena and even biochemical phenomena and biological phenomena. And so, in other words, if the anthropic principle extends beyond physics, that to me seems that seems to tip the scales in favor of theism more so than a non-theistic interpretation. Now, the first person that I was aware of who suggested the possibility of an anthropic principle that goes beyond physics into chemistry and biochemistry and biology was Michael Denton in his book Nature's Destiny. And Denton is a molecular biologist from New Zealand. I'm not sure what his religious orientation is. I'm under the impression that Denton is an agnostic. But in this book, which was published in 2000, it's a classic work in my opinion. He basically, again, argues that the anthropic principle does go beyond physics. That again, we see anthropic coincidences in chemistry, biochemistry, and biology. This book was strongly influential in my thinking about this idea of the anthropic principle going beyond physics. But what's interesting to me is that Denton didn't really originate this idea, because Denton's book is actually based on an earlier work published in the early 1900s, I think 1912, called The Fitness of the Environment by Lawrence Henderson, who was at that time a physiologist at Harvard University. And Henderson's claim to fame was working out buffering in the blood and working out buffering in the cytoplasm. And for those of you who had any kind of medical school biochemistry, you probably are familiar with the Henderson-Hasselbalch equation. And so this is Henderson of the Henderson-Hasselbalch equation. But as Henderson was working on the carbonate bicarbonate buffering system in blood, as well as the buffering system in the cell, which is based on phosphate salts, he became deeply impressed with the seemingly unique fitness of the chemical environment of the universe. And he basically argued in Fitness of the Environment that water, carbon dioxide, and organic compounds have this highly unusual and unique set of properties that are exactly what are needed for life to be possible. And that if we were in a universe without these materials, or if these materials had differing properties, then life simply couldn't exist at all in the universe. In other words, he saw that there was a unique fitness of the environment in such a way that, again, life could be possible. Now, Henderson was a non-theist, as far as I can tell, and yet he argued very strongly that teleology has a place in the biological sciences. This is interesting to me because the Darwinian revolution kind of stripped teleology from the life sciences, and Henderson was arguing that that was a mistake, that there is a place for teleology in the life sciences, where he saw the fitness of the environment as a complementary concept to Darwin's idea of the fitness of organisms for their environment. But he argued that if it wasn't for the fitness of the environment, then there's no way that life could originate and evolve in such a way to be fit to the environment that it lives in. Henderson's ideas were largely ignored at that time. And it really was about a century later that people began to revisit his ideas and began to start to make a much more robust scientific case for his ideas. And so there is a collection of essays called the Fitness of the Cosmos for Life, where it's a celebration and an extension of Henderson's ideas. And after reading through that book, I was really inspired to begin to do the work that is now represented in the book Fit for a Purpose, where again I ask the question, does the anthropic principle extend into biochemistry? Now, one of the things that was extremely valuable for me as I read through Henderson's remarkable book, and by the way, you can, this is in the public domain now, you can actually get a copy of this book on Amazon, and I highly recommend it. It's absolutely remarkable to read Henderson's ideas and his ideas about, again, the chemistry of water, the chemistry of CO2 and of organic compounds, because he was writing these ideas before theory of chemical bonding was established. And so his ideas are incredibly prescient and insightful for that time. It's really a work of genius as far as I'm concerned. But one of the things that Henderson does is he lays out a methodology that is extremely helpful in terms of establishing whether or not you see anthropic coincidences and hence an anthropic principle in different areas, in different regimes of complexity within the universe. And it's helpful towards that end to think about methodologically, how are people arguing for an anthropic principle in cosmology? And then how did Henderson argue for that in chemistry? And because this is going to be the criteria and the methodology that I'll use, that I use in the book and that I'll use this evening. And if you think about it, in cosmology, there are three criteria that people are using to argue for an anthropic principle. The first is that the constants that define the universe essentially arise out of the very nature of the universe itself, and that the value of those constants are precisely what are needed for life to be possible, and that those constants appear to be uniquely suited for life. Now, in cosmology, you're establishing the anthropic principle through theoretical analysis, through a type of counterfactual analysis where theoretically you're looking at the impact of varying the fundamental constants of nature, and again, the impact that this has primarily on star formation and the production of chemical elements. But these are the three criteria that are being used to establish, again, the anthropic principle in cosmology. And in effect, this is the three criteria that Henderson used, which is to look at the properties of key chemical systems, and again, recognizing that these properties are fundamentally dictated by the laws of nature, and that the properties of these systems are precisely what are needed for life to be possible, and that these systems appear to be uniquely suited for life. And so I'm just going to illustrate this very quickly by talking about the chemistry of carbon. And carbon, of course, is the chemical element that is used as the foundation for biomolecules. And carbon is ideally suited as the chemical element that is the foundation for biomolecules, because carbon has an incredibly rich chemistry. I think in the Beilstein's compendium, there's probably about 10 million entries for organic compounds, which is remarkable. And this is just a reflection of, again, the rich chemical diversity. And this is possible because carbon has the capacity to form 4 chemical bonds, but those chemical bonds can be single, double, or triple bonds. And this creates both structural as well as functional diversity for organic materials. Carbon is capable of forming stable chains and rings, which gives structural diversity. It's capable of engaging in a special type of bonding called aromatic bonding, which is critical for living phenomena, and also can form stable bonds with heteroatoms like nitrogen and oxygen, sulfur, phosphorus, the halides, as examples. And this gives functional diversity to organic compounds. And so the complexity required for life is easily satisfied by the structural and functional diversity available to carbon-based compounds. So, carbon, again, is this ideal atom for forming the basis of life. The question then becomes, are there any other chemical elements that would be comparable to carbon? And of course, if you look at a periodic table of elements, the element that is most likely to be a competitor to carbon in terms of its capacity to support life would be silicon. And this is because silicon is right below carbon in the periodic table of elements. So any element that is in the same column is going to have similar chemical and physical properties, where those chemical and physical properties vary in a predictable and continuous way as you go from the top of the column to the bottom. And so of all the elements in the periodic table, silicon has the greatest chance of forming a life, of being a life support atomic system. And the bottom line, and I'm not going to go into the details tonight just for the sake of time, but there are very good reasons why silicon is not suitable as a life support element. And some of those reasons are just bulleted here. I'm not going to talk about them. If people want to discuss this, we most certainly can. But the bottom line is that, again, silicon is superficially similar to carbon, but fundamentally is chemically distinct enough that the difference between silicon and carbon really is problematic for any kind of silicon-based life. Just recently, in 2020, in a journal called Life, a research team did a reassessment of the capacity of silicon to support life. And this is what they concluded, that silicon and carbon are false twins. Their similarities are superficial and insufficient to mitigate their crucial differences. Chemistry that is stable and normal for carbon is unstable and exotic for silicon. And similarly, chemistry that is unstable and impossible for carbon is stable and routine for silicon. Silicon's distinct chemical characteristics and reactivity make it a challenging choice for life. And so, in other words, what we see with carbon is that carbon, again, has chemical and physical properties that are fundamentally dictated by the laws of nature. The properties of carbon are ideally suited to make life possible, and that there doesn't appear to be any kind of alternative system that could supplant carbon, that carbon seems to be unique. And so, in other words, it satisfies the criteria for the anthropic principle. And what's also interesting is that there are other anthropic coincidences that are a bit eerie when it comes to carbon. Carbon, as it turns out, is one of the most abundant atoms in the universe. Next to helium and hydrogen, which are formed at the beginning of the universe in the Big Bang event, carbon and oxygen and nitrogen, which are critical elements for living systems, for life, are the most abundant atoms in the universe. And so it's interesting that those elements that are necessary for life, uniquely suited for life, actually are at a very high level of abundance relative to other atoms. And it turns out that the formation of carbon in stellar furnaces is produced through something called the triple alpha process. And this process is exquisitely fine-tuned. The nuclear energy levels of helium, beryllium, carbon, and oxygen must be exquisitely fine-tuned for this production process to take place, as well as fine-tuning in the strong force and Coulombic forces as well. So what you're looking at here is, again, carbon has this unique set of properties that arise out of the fundamental laws of nature. It's precisely what is needed for life to be possible. There's not suitable elements. And again, we see these eerie anthropic coincidences on top of that with respect to the elemental abundance of carbon in its production. So you see, again, evidence for the anthropic principle in chemistry illustrated through, again, the chemistry of carbon-containing compounds. And this is the type of analysis that Henderson did in Fitness of the Environment. So the question then becomes this. We just kind of summarize this point. The question then becomes this: is there an anthropic principle in biochemistry? And so again, we could use a similar set of criteria. Are the molecular systems that we see specified by the laws of physics and chemistry? And what I mean by that are these systems fundamentally dictated by the laws of chemistry and physics? Are they prescribed by the laws of chemistry and physics? Are they constrained by the laws of chemistry and physics? And then the question is, do these systems have those properties that are needed for life? And are there alternative biochemistries that are possible? So these are the three criteria that, again, we will use to assess whether or not biochemical systems display these anthropic coincidences. And in the book Fit for a Purpose, the systems that I've chosen to explore, to apply these criteria to, are proteins, nucleic acids, and phospholipids. These are three very important classes of biomolecules. And then I also look at four metabolic processes: protein synthesis, DNA replication, and then central carbon metabolism and the electron transport chain. And in my assessment as a biochemist, these would be the core biochemical systems. And so if you're going to see any evidence for anthropic coincidences, it's going to be in these core systems. In addition to that, if you look at the criteria for minimal life, that criteria would be having the capacity for DNA replication, protein synthesis, some type of energy metabolism, and the ability to form a cell envelope or a cell wall. And those minimal biochemical, or those minimal systems for minimal life, are essentially encompassed in these systems that we're going to look at for the anthropic principle. Now, there's not time tonight to go through all of these systems. And so what I'm going to do is focus this evening on proteins as a case study. And part of the justification for this is elaborated on by Michael Denton in an essay in a book called Fitness of the Cosmos for Life, where Denton argues that if the cosmos is uniquely fit for life as it exists on Earth, then given their primal significance, the proteins should be another uniquely fit ensemble of natural forms. In other words, what Denton is getting at is that if you're going to see the anthropic principle in biochemistry, it's going to be in proteins, if it exists at all, because proteins are of such central importance to living systems. They're the workhorse molecules of life. Virtually every cellular process, virtually every cellular structure involves an ensemble of proteins working collaboratively to carry out these activities to form these different cellular structures. And so if you're going to see the anthropic principle anywhere, it's going to be in proteins. And so I think for this audience, I don't need to necessarily do this, but very quickly, I'm just going to very quickly review the structure of proteins. And proteins are characterized by four different levels of structure. The primary structure, it would be the sequence of amino acids that form the polypeptide chain. There are 20 canonical amino acids that are used to build protein chains that are encoded by the genetic code. And these amino acids are linked in a head-to-tail manner to form a protein chain and the backbone of that chain can adopt different conformations. These conformations are referred to as the secondary structures. And the most prominent secondary structures would be beta-pleated sheets and alpha helices. And then these secondary structures can interact with each other to form folds and give a three-dimensional structure to proteins. And so this is referred to as the tertiary structure, which is the location of every atom in the protein in three-dimensional space. And then last but not least, there's a quaternary structure where individual folded protein chains can interact with other protein chains to form complexes. And what I demonstrate in the book Fit for a Purpose is you see anthropic coincidences at every level of protein structure. And I'm not going to discuss all of that tonight, but just give just a few examples of where you see these anthropic coincidences. And again, just as a quick review, this is the structure of an amino acid. And so the amino acid has a central carbon atom, and bound to that carbon atom is a hydrogen group, as well as what's called an R group. And it's the distinct nature of the R group that gives the amino acids their chemical and physical distinctives. And then there is an amino group and a carboxylic acid group bound to that central carbon atom. And this is a table showing the 20 amino acids that make up the canonical set. And the R groups, again, define the amino acid and have a range of chemical and physical properties that give a rich collection of chemistry and physics that are characterized by this canonical set, allowing the cell's machinery to build a wide ensemble of proteins with a wide range of structural and functional features. Now, the formation of the protein's primary structure, it depends upon a condensation reaction where carboxylic acid reacts with of one amino acid reacts with the amino group of another amino acid to form what's known as an amide bond or a peptide bond. So this is a condensation chemical reaction. And the peptide bond is a highly unusual bond that has a highly unusual set of properties. And it's these unusual set of properties that actually give proteins their structural and functional properties. So the protein structure, protein function is ultimately traceable back to the unique and unusual nature of the amide linkage. And this is essentially responsible for the anthropic coincidences that we're going to see in protein primary, secondary, and tertiary structures. And to appreciate how unusual the amide bond is, what we can do is compare proteins with their closest chemical analog, which would be polymers made up of alpha hydroxy acids. And so an alpha hydroxy acid has an OH group that replaces the amino group in an amino acid. And it turns out that this is significant for another reason, because if you remember the Miller-Urey experiment, right, where Stanley Miller, as a graduate student at the University of Chicago, sets up this glass apparatus that he evacuates all the oxygen from, and then introduces a flask of boiling water that presumably simulates the early Earth's oceans and has hydrogen and methane and ammonia in the headspace, and sends a continuous electrical discharge through the headspace to produce some amino acids in a few days to that experimental design, which at that time people heralded as a demonstration of the viability of chemical evolution. Most of the products that were actually formed in that experiment were alpha hydroxy acids. They far exceeded the levels of amino acids that were formed in the experimental design. And so if you assume that experiment is giving us any understanding about the early history of the Earth and the types of organic materials that would have been present on the Earth, the prebiotic availability of alpha hydroxy acids would be far greater than for amino acids. And so that in principle, if you're going to have some kind of chemical evolution, you would argue that just based on prebiotic availability and the close analog nature of alpha hydroxy acids compared to amino acids, that that polyesters made from alpha hydroxy acids could very well be the workhorse molecules of the cell instead of proteins. And in fact, the chemistry of carboxylic acids reacting with alcohols is very similar to the chemistry of carboxylic acids reacting with amines. In one case, you form amide linkages. In the other case, you form ester linkages. So it's very similar chemistry. And in fact, you can form, again, polyesters. This is an example of lactic acid, which would be the alpha hydroxy acid analog to alanine. You can form a polylactic acid, just like you can form a polyalanine. And again, in principle, you could argue that polylactic acid should be comparable to polyalanine because of all the chemical similarities. But the fact of the matter is there's a big difference between a polyester and a polyamide, and that difference has to do with the distinct difference between a polyester linkage and between an ester linkage and an amide linkage. And the fundamental difference has to do with the fact that an amide linkage has double bond character, where you don't see that double bond character in an ester linkage. And it's due to essentially the electronegativity difference between oxygen and nitrogen. That electronegativity difference actually produces a resonance structure for the amide linkage that has double bond character, that introduces double bond character in the carbon nitrogen bond. You don't see this same kind of double bond character in an ester linkage, and this double bond character makes the amide linkage highly unusual and is absolutely critical for establishing the secondary and tertiary structures that are so critical for protein function. So, for example, there are 4 consequences that are absolutely necessary for life that arise out of the double bond character. First of all, because of that double bond character, the amide linkage is much less susceptible to hydrolysis than an ester linkage. And the hydrolytic breakdown of a peptide bond would be the reverse reaction of the condensation reaction. And again, the amide linkage can undergo hydrolysis, but that process is much slower than it is for an ester linkage, which gives proteins an inherent chemical stability that is necessary for their functioning inside the cell. In addition to that, the double bond character actually imparts a rigidity to the peptide backbone. Because of that double bond character, you can't get rotation around the carbon-nitrogen bond, whereas the carbon-oxygen bond in an ester will have essentially a 360-degree rotation. And that rigidity of the backbone and the planar geometry of the amide linkage actually imparts enough structural integrity and rigidity to the backbone that when the protein adopts secondary and tertiary structures, those structures are inherently stable. Polyesters, because of that single bond character, are going to be highly flexible, kind of floppy molecules that will not form stable higher order structures, or they'll form highly malleable, highly flexible higher order structures, which isn't good for living systems. The double bond character forces a planar geometry to the amide backbone, to the amide linkage, whereas the polyester has a tetrahedral geometry. But that planar geometry and the double bond character actually sets up one of 2 possible molecular geometries. When you have a double bond with different functional groups associated with the 2 atoms that form that double bond, you can have alternative geometries that's illustrated here with This looks like let's see, there would be a 2-butene, where the two methyl groups are in one geometry are on the same side of the double bond. This is known as a cis geometry. And in the trans geometry, the methyl groups are located on the opposite side of the bond. And so with regard to the amide linkage, there can be a cis and a trans geometry, but the cis geometry is less thermodynamically stable than the trans geometry. And so the trans geometry is going to dominate in an amide bond. And this is actually highly fortuitous because the trans geometry puts the nitrogen bound to the amino group, the hydrogen bound to the nitrogen and the carbonyl group in the right orientations in space that allow for hydrogen bonding interactions that stabilize beta-pleated sheets and alpha helices. In addition to that, the double bond nature of the amide linkage creates steric constraints that actually reinforce the capacity of the protein backbones to form alpha helices and beta-pleated sheets. So this is, again, a small section of a protein chain, and there is a carbon atom there that's in the center of that chain. This would be the alpha carbon that binds the nitrogen and binds the carbonyl group. And those two bonds are single bonds, and because they're single bonds, they can actually rotate, in principle, 360 degrees. So even though the amide linkage has double bond character, what are known as the phi and the psi bond angles can assume, in principle, anywhere from 0 to 360 degrees in terms of their rotation. However, because of steric constraints, those psi and phi bond angles are constrained to only certain bond angles. And those bond angles are actually those bond angles that will produce alpha helices and beta-pleated sheets. And so this again leads to the formation of these secondary structures that are characteristic of proteins. This is what two biophysicists, Van Vanar and Martin, say about this kind of interesting confluence of properties that arise out of the double bond nature of the amide linkage. One cannot but marvel at how several factors, the steric interactions, hydrogen bonds, which provide the scaffolding for protein structures, the constraints placed by quantum chemistry on the relative lengths of hydrogen bonds and covalent bonds, and the near planarity of the peptide bonds, and the key role played by water, all reinforce and conspire with one another to place proteins in this novel phase of matter. So in other words, what you see here are this set of anthropic coincidences that are dictated by the laws of nature that are producing these just right secondary structures that are going to be necessary to build the three-dimensional structures of proteins. And so again, it's a bit eerie, but you begin to see a manifestation of this idea of an anthropic principle here, where again, the nature of the amide bond is dictated by the laws of nature and has very important consequences with respect to the formation of secondary structures, the alpha helix and the beta pleated sheet structures. Oops. Okay, now when it comes to higher order structures in proteins, when we start talking about tertiary structures of proteins, the next thing that we need to think about are what are sometimes called super secondary structures or protein folds, where the alpha helices and beta pleated sheets now in that protein chain, in the localized regions of the protein chain, can interact with each other in three-dimensional space to form folds or to form the beginnings of the tertiary structure of proteins. And to appreciate the anthropic coincidences that are associated with this higher order folding in proteins, we need to think about a concept known as protein space. And it typically refers to all the possible structures that would be available for a protein. And so, for example, if you have a protein that's 150 amino acids in length, there would be 20 to the 150th power possible amino acid sequences for proteins that are 150 amino acids in length. That's a vast amount of protein space. But this is just simply referring to the primary structure of proteins. When it comes to proteins, of course, it's the three-dimensional structure that's of interest. And so estimates are that a protein that's 150 amino acids in length can minimally fold into 10 to the 68 possible three-dimensional structures. There's 10 to the 68 possible folds, which means that when you're looking at protein space, you're looking at 20 to the 150th power, that raised to the 68th power. So it's a vast amount of possibilities, combinatorial possibilities for protein sequence and tertiary structures. But what's interesting is that biochemists have only found that there are a few thousand protein folds that exist in nature. And each of these folds actually displays a wide range of functionality, and that different amino acid sequences will adopt the same fold. And this all suggests that there must be some kind of physical chemical constraints on the ways in which secondary structures can interact to form protein folds. And in fact, we just made that point. And this makes sense because when you look at the way, for example, alpha helices interact, there's only certain ways that alpha helices can interact with each other that are topologically possible. And in fact, a famous protein chemist by the name of Kothia in the late 1990s said this, that the helices and sheets pack together in one of a small number of ways. The connections between secondary structures obey a set of topological rules. In other words, the folds that form these supersecondary structures in proteins are fundamentally constrained by the laws of nature. And it's interesting that these folds, again, can adopt a wide range of functional characteristics, and different amino acid sequences can form the same folds, which imparts that range of functionality to these folds. And so, again, we begin to see these anthropic coincidences that emerge. Now, along these lines, there was a study done by Banvanar and Martin, which I mentioned earlier, two biophysicists that I mentioned earlier. And they did this really interesting theoretical characterization of protein folding. And what they did is they argued, assume that each amino acid is a disk, and that you could then tether the disks together to form a tube-like structure where there's flexibility to the tube so that the tube can fold back on itself, and will do so in such a way to exclude water from the interior structure of this folded tube, where the only distinction between the disks that form the tube would be the hydrophobicity or the hydrophobic profile of that tube along the tube geometry, or the hydrophobicity of the individual tubes. And what they did then was they established a quantity called the folding parameter, which is the ratio of the tube diameter to the the range of the attractive interactions as that tube folds back on itself. And to get a sense for the folding parameter and what it's telling you, if you have a very, very large folding parameter, it means that the tube is really fat. And if it's fat, it can't really fold back on itself. The diameter is much greater than the range of self interactions. And so the tube can't fold. if you have a very, very small folding parameter, it's like having a string, and that allows for a near infinite number of ways that that tube can fold. There turns out to be a sweet spot where the folding parameter is approximately 1. And in this sweet spot, you get about 1,000 folds, where you have a balance between attraction and steric constraints. And it turns out that when the folds that you produce in this system are identical to the folds that you see in proteins, and it turns out that the folding parameter for proteins is actually 1. And so this is rather remarkable. But this regime where the folding parameter is in effect 1 is a special circumstance because it is in effect represents a type of transition point or a type of critical phase where you have this balance between self-attraction and steric constraints. And what that means is that for tubes with a folding parameter of 1, because there's a limited number of ways it can fold, it allows for those folds to very quickly form. And so this, in a sense, because the folding parameter of the protein chain is 1, this in effect solves the Leventhal paradox, which is how is it that proteins can fold so rapidly into their native state structure, given all the possible ways that a protein could fold? Well, because of the geometry of the chain, it actually leads to a limited number of folds, which makes it very easy to find the native state structure. It also gives, because there's this tenuous balance between attraction and repulsion because of steric effects, that it gives conformational flexibility to the three-dimensional structure of the fold, which is necessary for proteins to carry out their activity inside the cell. It also means that these folds are robust to mutations, and it also allows for a wide range of different amino acids to form the same folds, which gives a wide range of functional properties to the folds as well. This is what Banvanar and Martin say. The common belief is that given a sequence of amino acids with all the attendant details of the side chains and surrounding water, one obtains a funnel-like landscape with the minimum corresponding to its native state structure. Each protein is characterized by its own landscape. In this scenario, the protein sequence is all important, with the protein folding problem needs to be attacked on a protein by protein basis. Protein folds do not evolve, rather. The menu of possible folds is determined by physical law. In that sense, it's as if evolution acts in the theater and the shapes and sequences and functionalities, but does so within the fixed backdrop of Platonic folds. In contrast, our model calculations show that the large number of common globular proteins reflect a deeper underlying unity in their behavior. This landscape is pre-sculpted by general considerations of geometry and symmetry. So again, you see these anthropic coincidences at the level of the tertiary structure of proteins. Now, in the book Fit for a Purpose, I talk about this anthropic coincidences that we see with active sites and protein binding sites, as well as with the quaternary structure of proteins. I'm not going to get into that this evening just for the sake of time, but I am going to revisit this question of why amino acids and why the particular 20 amino acids that form the canonical set. So we're going to kind of return back to the primary structure of proteins. And as we already pointed out, you can't have an alpha hydroxy acids that are used to build proteins. You have to have amino acids. Now, in principle, you could build proteins with diacids and diamines. In fact, this is how nylons are formed through industrial chemistry. And nylons are kind of a synthetic version of proteins. But the problem here is that you would have to have 40 molecules that form the canonical set, not 20, because you'd have to have corresponding diacids and diamines in order to build protein chains. So the level of complexity of that system far exceeds the simplicity of the using 20 amino acids. You can't have beta, gamma, delta, or N-alkyl amino acids because none of these will form hydrogen bonding interactions needed to stabilize secondary structures. You have to have a hydrogen on the alpha carbon. If you have any other chemical group, it creates steric effects that impact protein higher order structure. And as it turns out, the set of R groups appears to be a highly optimal set of R groups. These 20 canonical amino acids possess chemical and physical properties that vary uniformly across size, charge, and hydrophobicity. And a biochemist by the name of Stephen Freeland compared the canonical set of amino acids with random sets of amino acids and basically showed that the canonical set that we see in nature is unique in terms of its optimal nature compared to random sets. And so in other words, every level of protein structure seems to again manifest the anthropic principle that because of the unique nature of the amide linkage, which is fundamentally dictated by the laws of physics, you have as a consequence protein secondary and tertiary structures. These are fundamentally constrained and dictated by the laws of nature, and that these are systems that have precisely the properties that we need for life, and that you cannot conceive of alternative biochemistries based on protein chemistry. There doesn't seem to be alternatives to protein chemistry. And in fact, we could go through the other biochemical systems that I talked about and do a similar type of characterization and wind up with the same conclusion that these seem to be, again, highly unusual systems that very well may be unique in their capacity to support life, and that the fundamental properties of these systems that are critical for life don't seem to be the outworking of a historically contingent evolutionary process, but rather seem to be fundamentally dictated and prescribed by the very laws of nature. And so, in other words, there seems to be an anthropic principle that is manifested in biochemical systems, as well as in chemical systems, as well as in physics. And so that, to me, is rather provocative. And scientifically, it's significant in the sense that it's telling us something fundamentally about the nature of biochemistry, and that the fact that there's actually the set of physical and chemical constraints on the structure of biochemical systems suggests that you might actually have law-like behaviors that might emerge that provide us with a framework to explain biochemistry. That is, there might be something compatible in biochemistry similar to chemical bond theory that you see in chemistry that actually allow us to develop fundamental predictions about the nature of biochemical systems. Also, this has implications as well for the search for life beyond Earth, because it's very commonplace for people to argue that there are possibly alternative biochemistries that could support living systems. And I think that's actually a flawed way of thinking, that in other words, terrestrial biochemistry seems to be universal. There seems to be a universality to biochemistry, but there's also, I think, a theological and philosophical significance as well to this, in that there very well could be a divine conspiracy that is responsible for these anthropic coincidences that we see in biochemistry. And if that's the case, then it means that that teleology should be front and center in the way that we think about the nature of biochemical systems. and that this could also be used as a way to marshal a case for a creator being responsible for life. And what I like about the anthropic principle is that it actually creates the means to begin to bridge the position that I hold, which is an old earth creationist position, with at least some versions of theistic evolution, that it represents kind of a bridge between those two perspectives. So anyway, I'm going to go ahead and end my presentation here and really open up the floor to questions and comments. But I think it'll be a lot of fun just to kind of talk about what the implications of this are, if indeed there is an anthropic coincidence.
Thank you very much. I really appreciate the presentation. I'm not a chemist, so I didn't understand all of it, but I did have a couple questions. I'll ask one now. I know with cosmological fine-tuning, I've seen, I think, some numerical estimates like, well, the chances of this happening by chance are astronomically low. Is there an analog with your presentation? Like, is there a way to get a sense of just how unlikely this would be in the absence of a designer?
Yeah, well, the chances of some, the probability calculations that you're referring to are usually in association with things like the rare earth hypothesis, right? And this is kind of based on a Drake equation. But typically what you see for the cosmological anthropic principle is not really probabilities. What is the probability of, the ratio of the gravitational to the electromagnetic force constant being the value that it has? But rather what you're doing is you're saying that if that value deviates ever so, as little as 1 part in 10 to the 40th power from the value that it assumes, life isn't possible. So it's a quantitative assessment, but it's not based on probabilities.
Okay.
The probabilities only show up in the rare earth context. Now, in chemistry and in biochemistry, it's a qualitative comparison that you're making, but it's actually more robust because it's experimental, right? These are experimentally determined comparisons. So, for example, it's not a theoretical assessment of, when we're comparing polyamides to polyesters. That's experimental work that we're doing, right? And so while it's qualitative, it's actually, I would argue, a more robust conclusion because it's experimentally driven, if that makes any sense.
Yes. So,
there are places where you can do numerical assessments, like, again, with the folding parameter that Van Mar and Martin developed. But typically, it's a qualitative comparison.
Great. Thank you very much.
Cy, you're up next, and then Nick after Cy.
Thanks. Thanks, Fuzz. That was a great presentation. I really enjoyed it. I do have one sort of general question about the question of physical laws and, the anthropic principle of the fine-tuning. And that is, you made a really strong case for physical and chemical laws that lead to, proteins being the essential, having the essential properties that they have. But my question is, do you think that there are biological laws in addition to these physical chemical laws that are unique to biology? And by that, I'm thinking of the way that, some of the more complex processes that go on in some of the systems that you put on your slide, like protein synthesis and energy conversion. Those systems are not found outside of biology. They're not found outside of biochemistry. And do you think that there are unknown, at this point, laws? And I think Denton has said something like this in some of his books as well, reflecting the work of Owen, do you think that those might also be hiding somewhere that we should look for and perhaps see if we can discover them? And my own view is that yes, there are, and they're going to be very much related to teleology. But I just wonder how you think about it that way.
Yes, I would share the same view as you, Cy. I think there are these hidden laws of biochemistry that and this, I think, is the value of this analysis that I did, trying to make a case for the anthropic principle, is that it begins to suggest that these laws are there, right? That you're seeing this deep-seated rationale that seems to undergird, biochemical systems, which suggests that there are these laws that are waiting to be discovered.
Okay.
And boy, that would fundamentally change the nature of biochemistry, because biochemistry is largely descriptive. I mean, it's, you're dealing with, highly sophisticated scientific work to characterize these systems, but a lot of biochemistry has really been descriptive,
right?
As opposed to, as opposed to something like you see in organic chemistry, where with chemical bonding theory, organic chemistry isn't descriptive. It's, you're applying those laws to, and so when it comes to the work that's happening in synthetic biology, it's highly driven by trial and error, as opposed to driven by some kind of understanding of laws that you then apply to create, novel, life forms. So I think those laws are there, and if they are there, it really has, profound teleological implications, but very important scientific implications too.
Thank you.
Am I on, Mike? Hi. Fuzz, as usual, this was really incredible, and I really loved your book. One thing I've noticed about the fine-tuning argument is as it gets stronger, the resistance to it gets wider. There's a number of very intelligent scientists who have websites who really, they either try to deny fine-tuning in general, or they explain it in ways that are hardly credible. And this is mainly with cosmological fine-tuning. Every day it gets more and more. Now adding this layer on top, I assume we're going to see the same thing in the biological community, where the first wave is going to try to deny. I already know that from running your ideas by friends of mine who are in that field. But then over the long haul, they're going to have to deal with the fine tuning, which you can't deny. My question is, what a lot of us here on this meeting are after is not just to make a teleological argument, but connect it to God. So connecting it to establishing teleology, to getting it to God, to getting it to the God of the Bible, to getting it to the God of Christianity is a long haul. And we need to keep that in mind. My question to sum this up is, why doesn't somebody like Michael Denton, whose books impressed me as it does you, why does he continue to resist, at least openly, acknowledging God? And that's really where we're going with all this.
Yeah, I don't know that I've got any type of insight that's helpful, right? Other than, when it comes to fine tuning, for somebody who's a theist, it's, it seems to be such compelling evidence for, a creator that's intentionally put the universe together in this way. But the loophole is, basically a multiverse, right? That we just happen to be in the lucky universe. And so that is a possible interpretation of it. But, it seems to me, and I don't know that I could defend this rigorously, but intuitively, it seems to me that if you start seeing anthropic coincidences manifested at different levels of complexity in the universe, not only in the physical constants, but again, in chemistry and biochemistry and biology, that to me seems to tip the scales in the direction of theism more so than I think than a multiverse. But I mean, the anthropic coincidence, principle is very provocative, but it doesn't compel necessarily theism. And so somebody to offer a multiverse interpretation isn't necessarily unreasonable.
Well, yeah, that's where I would differ. I think the multiverse only can go so far, but the challenges to the multiverse are such that it would undermine that argument for what you're presenting here. Right. Because these are contingencies and complexities and things, and at some point they know they're just doing it because they can. It's sort of denial, and that's not going to fly very far. That's why I think we should continue to press on in this area. I think it's going to be very fruitful.
Well, ultimately, Nick, and this was, I think, Barrow and Tipler's point, is that, that the strong anthropic principle is again indicating that the universe is an imperative, right? That there's something that's dictating the universe to be this way. And whatever's dictating it is beyond the universe itself. So it's either a multiverse or it's God, right? It's a personal God. And so, take your choice. But in a sense, now the multiverse explanation and God as an explanation are in a sense equivalent explanations. They're on the same footing, right? And the multiverse is just a materialistic explanation versus a theistic explanation. But everybody's got to posit something outside the universe that has brought the universe into existence and has made it this way, right? So at minimum, it elevates theism to a viable alternative, a viable explanation. And of course, if you're going down the materialistic route, you've got to come up with some kind of, way to test whether or not the multiverse exists. And that, of course, is, kind of is contentious as to whether or not the multiverse is actually a bona fide scientific idea in that it's actually testable, right? So it has the dressings of of science, but is it really science in that sense? So.
Hey, Fuzz, I've got a question for you.
Sure.
I'm going to read a part of your book here on page 309. It says, if constraints exist that arise out of the laws of nature and dictate the structure and function of biochemical systems, as the biochemical anthropic principle demands, then it becomes reasonable to regard the origin of life, and consequently the origin of biochemistry, as a highly probable, if not inevitable, outcome of evolutionary history. In this scheme, the origin of life cannot be considered an outcome that reflects mere happenstance. Instead, it becomes an imperative. So it seems to me that this exquisite molecular logic that you mentioned, these scenarios reduce the odds of abiogenesis to 100%, given the right location and the right prebiotic environment. And this is something that I agree with wholeheartedly. But a few pages later on 316, you state that there is direct empirical evidence that a creator must have intervened to bring about the origin of life. So I'm having a hard time, there seems to be a little bit of a tension there, and I'm trying to thread the needle here with that. What kind of direct empirical evidence is there that you see that the creator must have intervened, yet at the same time, it seems that abiogenesis is an imperative in a paradigm in which God intended life to arise in the cosmos at some point in time?
Yeah. So, you're talking about the chapter where I start thinking through what are the implications of an anthropic principle. And as I mentioned earlier, this is an idea that I think someone who is a theistic evolutionist and someone who's an old earth creationist can both embrace. And so it becomes a bridge position. So what I was doing in that chapter was saying, look, if if you hold to some version of theistic evolution, this anthropic principle indicates that that the universe was probably rigged in such a way that life becomes inevitable, right? That the whole thing is a rig job, right? That's a legitimate way of looking at it. As an old Earth creationist, you would say, well, this suggests design, and to me, what I think tips the scale in favor of more of a kind of an ID old Earth creationist perspective would be the work that is taking place, or not the work, but the struggle that is emerging out of work in prebiotic chemistry, where the researchers in this area are now becoming deeply concerned about what's known as unwarranted researcher involvement. This was actually the theme of my book, Creating Life in the Lab, and that was published in 2011, which is this idea that when researchers are going in the lab and doing experiments in prebiotic chemistry, they're doing these experiments under highly contrived, highly controlled conditions, and to the point where the researcher's involvement in the experimental design, in effect, is influencing the outcome of the experiment. And that under the conditions of the early Earth, that you would not have researchers available to rig the system in such a way to ensure productive chemistry on the surface of the Earth. And so that, to me, becomes an empirical demonstration of the necessary role of intelligent agency in generating the origin of life. And so that's why I would make that statement. So, and this is where it really becomes a bit messy, where, again, there's a number of possible ways to make sense of this. Now, something that I ran out of room in the book. Our editors basically put a word count restriction. Otherwise, there would be a chapter in the book about the anthropic coincidences connected with prebiotic chemistry. But since the book has been published, I've written a few blog articles where I began to explore this. And something that is really impressive to me is relating to the Krebs cycle. I mean, in the book, I talk about just the optimal nature of the Krebs cycle, that it's this just right, metabolic system that sits at the hub of intermediary metabolism, that the intermediates that are part of the Krebs cycle are these just right intermediates with these just right properties, and that you can't conceive of alternative Krebs cycles. People have tried to produce alternatives to the Krebs cycle and have failed, right? That the Krebs cycle really stands out as this highly optimal system that's perfectly designed to do what it does. But what's interesting is that Harold Morowitz was the first to recognize this, that the material, the intermediates in the Krebs cycle seem to form this highly unusual set of compounds. That he started with Beilsteins and developed this set of filters to select compounds that could conceivably be present on the early Earth, that essentially would be conceivably be formed under the conditions of the early Earth. And out of 10 million compounds, he winnows it down to about 150 compounds, and the Krebs cycle intermediates are in that group. And he was arguing that there seems to be something really suspicious going on here, that the conditions that would have been available on the early Earth would be precisely the conditions that would produce these Krebs cycle intermediates, right? And that that this is also a conspiracy between the conditions of the early Earth and the nature of carbon chemistry, that they can conspire together to produce these compounds that, again, would be ideally suited to form the Krebs cycle. And just recently, there's been a number of experiments done in prebiotic chemistry where if you start with glyoxylate and pyruvate and throw it into water, you wind up generating the Krebs cycle. You wind up and the production of the intermediates sequentially goes in accordance to their position in the Krebs cycle. It just happened. It's just water and glyoxylate, water and pyruvate. Earlier studies showed that you needed like an iron catalyst, and subsequent studies show that you don't even need that. So that's really and then the same thing is true with the glycolytic pathway, that you start off with a single compound, and the glycolytic intermediates actually naturally form under conceivable prebiotic conditions. So this is really interesting that these two metabolic pathways that are central to life just seem to fall out of the chemistry that of carbon compounds and what would be possible under the conditions of the early Earth. So it almost seems like there are these anthropic coincidences connected with prebiotic chemistry as well, which again leads to this idea that maybe the origin of life is this imperative, and that the universe is rigged in such a way that life could be possible. But yet you still have this problem that even if you have these building block materials, how do you generate, for example, information-rich polymers, right? It's one thing to get RNA molecules, for example, to assemble on a glass surface in the lab or on clay surfaces in the lab. But when you look at the nature of those experiments, they're highly rigged to ensure the successful generation of those polymers. And to conceive of how that would happen on the early Earth in a productive way is really a challenge. And so it seems like, at least with regard to the building block materials, there looks like there may be these anthropic coincidences at work as well. But to go from that collection of building blocks to actually bona fide biochemical systems, to me, seems like you've got to have intelligent agency involved. And so that's why I think you still need a creator involved. So to me, the way I would look at it is that the puzzle pieces will naturally form, but to assemble that puzzle requires the involvement of a creator, right? So anyway, that's how I resolve that tension. But again, to me, to say that there are these anthropic coincidences and that the origin of life is an imperative, and that the outcome is going to be inevitably exactly the way it is now every time that the origin of life happens, that to me is not your grandfather's chemical evolution. That is a highly teleological version of chemical evolution, which I would be completely comfortable with. As an old Earth creationist, I would be completely comfortable with it.
All right. Thanks, Fuzz. Nick, you have your hand up.
Yeah. One of the common responses is that life has adapted to what it's been given, the environment it's been given, kind of like, a stream forms because of the ravine that is there. It seems like the level of details and complexity make that argument harder, but can you just comment on that and how to deal with that one?
Yeah, well, or this is kind of like the puddle analogy, right? You pour water into a puddle, and the water says, "Wow, that the shape of the puddle is perfectly perfectly suited for the shape of the puddle, right? Or the shape of the water in the puddle." And I think that it misses the point, because what the anthropic principle is really saying is not that life is not that the shape of the puddle is significant. It's the fact that you could even have a concave surface at all, right? It's eerie that we live in a universe where concave surfaces are possible, and therefore a puddle can form, therefore life can form, right? And I think it's the same idea when you start talking about a chemical and even a biochemical anthropic principle. It's it's not that life just simply adapts to what's available to it. It's that the fact that you can't even get that life to exist if it wasn't for the anthropic principle manifesting in chemistry, and I think in biochemistry as well. I don't know if that really addresses your question or not, but
No, I think it does, but it's one of the most common things that come up is after you do a full presentation like this, and it's seen like, boy, how am I going to argue with that? That's all facts. The next thing is, well, of course, life is going to adapt to that. So I think it's good to have a response and a thought out reason for, your thinking on that one. So good. Yeah, I was fine with that.
Anyone else out there on the line have a question or observation? All right, Nick and Fuzz, I want to bring you into. Was that Bob? Did you have a question? You're muted right now. There you
Sorry,
go.
can you hear me?
We've got an echo. You may have two devices going on right now, but
Try and get rid of one of them.
okay, sounds good.
So I heard very recently a discussion of comparing cellular level activities to finite state machines. I think it was just on Star Cells and God a few days ago.
yeah.
And I associated that in my mind with a topic of sometime in the spring in which you were discussing a team that has produced synthetic cellular action, modeling the minimum viable cell using computer software. It seemed like those two are related to each other, and they seem to imply that those processes inside of the cell are completely deterministic. Otherwise, you couldn't write software code to mimic it. And the thought that was raised by that in my mind is, I wonder if a naturalist could then say, by extension, even neural processes are a more complicated version of what you've done in software, that ultimately neurology, those processes are also completely deterministic, and there's no such thing as volition. You see where that takes you. Where do you break that chain where it's no longer completely deterministic?
Yeah, wow, that's a great question. Well, I mean, I think there's a number of people that would hold to a materialistic perspective that would make that very type of argument, right? That it's ultimately deterministic. But I think what becomes the killer when you start talking about that at a neurological level is that if you then are stripping away the free will, right? You've completely undermined the idea of free will. And if that's the case, then free will at best becomes an illusion, but there's no such thing as free will. Then if that's the case, then it means that you're not ultimately making any kind of choice on your own volition. Everything has been ultimately predetermined by essentially chemical and physical processes, right? So I think that's the once you start getting rid of free will, I think you ultimately undermine the whole scientific enterprise, right? The conclusions that you're drawing about the world around us is not necessarily the conclusions that flow out of deliberation and contemplation. It's just simply, this is the deterministic outcome of neurochemistry. So,
right.
so to me, I think the point being is that at a cellular level, you could have deterministic processes. You could have deterministic processes at an anatomical and physiological level. There might even be deterministic processes going on in terms of brain activity, but the only way that you ultimately escape that is by arguing that there must be something that's immaterial about us as human beings, which would be essentially our mind or the spirit or whatever, the soul. So there has to be some kind of immaterial aspect to our nature. That's the only way you escape that otherwise everything is deterministic.
The pejorative term for that is the ghost in the machine.
Yeah.
Which is usually not expressed as a philosophical viewpoint, but rather as a criticism. But from the physiological side, is it possible for something like quantum randomness or something non-deterministic in physics to add something other than a deterministic flow to those cellular processes, especially neurological?
Yeah, I don't know. I don't know how to even approach that question. Yeah. It's a great question.
It seems like what the trick is that it seems like these experiments and being able to model cellular function with software open up the possibility for someone to argue from experimentation that cellular processes are all deterministic. And we can counter that with a philosophical argument, but is there any physiological argument to counter it?
Well, this is a really important question for that impacts things like the transhumanist vision, right? Because in the transhumanist vision, the idea is that eventually we're going to be able to upload our memory and our the essence of who we are into some kind of machine framework, right? And there you're simply treating, again, the brain precisely as a computer, where memory is like data, and like the processes that go on in our brain are like software operations. And yet I don't know that you can, while we might be able to, from a neurochemical standpoint, have some kind of understanding of the processes that are involved when memories form, when memories are retrieved, while we can tell that a memory is being encoded, a memory is being retrieved, we can't tell what that memory is, right? And what precisely is being stored, what precisely is being retrieved. We can tell that people are thinking, but we can't tell what they're thinking, right? And so this is where the computer analogy starts to break down, I think, and where you start to push into kind of the necessity of having some kind of immaterial nature to human beings.
Thanks for your question, Bob. Sai.
Yeah, I actually wanted to address that question, if I may. I'm pretty strongly in the opinion that we're not going to be able to model cellular physiology algorithmically. And there are a lot of reasons for that. One is that, yes, there are stochastic processes in cells. And I think one of the most important, for example, is the quantum tunneling that goes on during the production of energy, during the conversion of light energy into ATP. The electrons actually act in superposition. They choose different paths at the same time to go down to get the most efficient energy production, which is really strange. And this is a discovery that's only a few years old in photosynthesis. That's one example, but there are many other examples of non-computability in biology. And since you raised the issue of neurology, there's this idea that consciousness is by its very nature incomputable, which was presented by Roger Penrose, a very famous physicist. And he claims that using Gödel's theorem, which is this the theorem that applies to mathematics, but can also be used to understand what we can know and what we can't know. He claims that consciousness cannot be computable because we would never be able to. Well, I'm going to get lost in the description, but because it's over my head. But his claim is that by using that principle of non-computability, he can say that being conscious means that we can't define consciousness as a computable thing. And in fact, we can't define consciousness at all. And I think there's something in that fact that would lead us to agree with what Buzz said, which is that it's not going to be computerized. It's not going to be something that we'll never have an AI that's equivalent to a human. And there are many people in the field who agree with that. So, but when you talk about cell physiology, there's something else besides strict determinism, which is that there's a lot of chaotic processes in cell physiology. Now, those are deterministic, but they're not predictable because of the difficulty in finding, all the factors that go into determining any physiological system. So it's kind of like you have, as Fuzz was talking about, it's kind of like you have laws which are telling us that certain things are going to happen, but at the same time, when you look at the details, there's a huge amount of variation that's possible. And that kind of is the definition of life, okay? Because life is not robotic. It's extremely adaptive. It can change all the time. It's very stochastic. And I personally am very skeptical of the idea that any algorithmic advance will be able to really mimic life. It hasn't happened, and I don't think it will. Not at the basic level. But that's my own opinion. I don't have proof of that.
I think that the study where people created this, system where they could simulate cell activity, this was based on the minimal cell that Craig Venter developed, and they were developed basically a way to again simulate and predict cellular processes. You're looking at it stochastically, as you're saying, Cy, right? Where you can't tell what's going to happen with individual molecules, but collectively, you know that this is going to be approximately the level of gene expression, right? So you can do it stochastically, but not at an individual level.
Yeah, and Craig, as you know, Craig Venter's cell was basically he didn't really make a cell.
Right.
Yeah, he kind of, he admits, he cheated. He took a nucleus and put it in a working cell and then, changed the DNA around. So, you can do stuff. You can make progress in that direction. The question is, how far can you go? And I don't think you can go all the way. If you could go all the way, we would have done it already.
I wanted to make a comment about the appeal to quantum mechanics, which is one I see. The deeper I look into quantum mechanics, the less of a place is to go to appeal like that. Because when you get there among the quantum physics themselves, with quantum field theory, particles are not even solid. They're just excitations in a field. And whenever they run up against a problem, they think of another field that they make up. I'm not criticizing it. They're really smart. But these fields and the laws that come out of quantum mechanics all come out of the math. It's all the math.
Yeah.
And then you have to add, well, where does the math come from? And this is quantum mechanics itself, the essence of that. So I just wanted to comment that quantum mechanics is not a good place to run to try to explain away or to try to find a materialistic understanding for things. If anything, it's only a deeper quagmire.
Yeah, I was saying it in terms of stochastic issues, not materialistic or whatever.
I agree. What you were saying, you made great points. I wasn't criticizing that part. Just quantum mechanics is not the escape route that many think it is.
Also, because perhaps if you try to add determinism plus randomness, that doesn't yield anything like volition.
Right.
Maybe you could say that quantum processes are truly random, but mix that with determinism, that doesn't give you any smarter result.
Right.
Well, my big clue was when the conclusion, those who study consciousness, they're willing to say there must be some consciousness field out there. It's just It must be out there, and it's an inevitable thing. Well, when they're getting to that level, then they're not giving any explanation at all.
Right.
That's not too far from the spirit, actually.
Yeah. When you when you really look at people who are criticizing fine tuning and consciousness and all of these things, materialistic view, you really should listen to what they say, because they just don't make sense at some point. And they actually become incoherent in their explanations. And I like these people. I follow them and everything, but they just aren't coming up with the goods. I think that you guys are. Fuzz, I think your book is really one heading in that direction. It's really, I think it's one of your what do you call it? A masterwork. I think it's really good.
Hey, Nick, I want to touch on something you mentioned at the beginning of the Q&A, and I'm hoping that Fuzz might be able to provide an answer. In Fuzz's book on page 307, he's talking about the metaphysical implications of the biochemical anthropic principle. Fuzz, you write, generally, scientists are uncomfortable discussing metaphysical implications, in part because of the influence methodological naturalism has on the operation of contemporary science. However, avoiding and sidestepping the metaphysical implications doesn't mean they don't exist, and it doesn't mean that we shouldn't explore them. Now, I'm a proponent of methodological naturalism, but I know that at the end of the day, you do have those metaphysical implications that are there that you have to address. But at what point does methodological naturalism stop being legitimate? Or is methodological naturalism not a legitimate way of conducting the scientific method at all?
Yeah, well, my particular view with regard to methodological naturalism is I would embrace a soft version of it, not a hard version of methodological naturalism. So I actually am of the opinion that science has the capacity to actually detect the work of intelligent agency in features in nature, and even draw conclusions about the nature of that intelligent agent. And so to me, I think methodological naturalism is a great starting point when you're investigating phenomena. But if the data is pointing in a direction that is teleological or suggests the work of intelligent agency, typically with hard methodological naturalism, you start drawing some boundaries about what types of models you can or can't present. Whereas in a soft version, you're looking for, materialistic explanations or naturalistic explanations, or natural process explanations, mechanistic explanations. But if the data is driving you in a particular direction that suggests agency or teleology, that you pursue that through science. So that would be my own personal perspective, is a soft form of methodological naturalism. But even if you adopted a hard form of methodological naturalism, when there are metaphysical implications to, the universe has a beginning, for example, or there's fine tuning to the universe, what you oftentimes will see people do is say, well, that, this is the boundary of science. I'm not going to address those issues because they fall outside the boundary of science. And the net effect is they act as if they don't exist, or they act as if they're unimportant, right? And so to me, whether you adopt a hard or a soft form of methodological naturalism, the metaphysical implications need to be dealt with. and making the claim that this is outside of the bounds of science and then kind of washing your hands of those implications isn't intellectually integrous, I think.
Thanks, Fuzz. Any other questions at all? Sai, you've got a thumbs up. I'm not sure if that was a hand raised or you're actually enjoying the discussion.
No, I just really like what Fuzz just said, so I want to do a thumbs up.
Sure. Awesome.
Mike, you said about methodological naturalism. Number one, methodological naturalism is based on denial, which is a psychological mechanism. It's almost like being an actor on a stage. You have to deny a lot of things to get into that state. I'm a scientist at the lab bench now. But now understanding what Fuzz is telling us about nature, even using the term naturalism, cannot deny in and of itself theism. And so the term naturalism to me doesn't in any way imply that there is no God at work. And the third thing is, when you walk into the lab, you're still you. The problem with science is it has to be done by human beings. And human beings are incapable of real methodological naturalism. Only a robot can do that. So for those reasons, I have a problem really believing in methodological naturalism, although I understand what Fuzz is saying with soft, he's being nice with that. Like as a physician, when you walk into my exam room, I'm going to look at your body like a mechanic looks at the car at some level. But at the same time, I'm a human being, and that's a human being. And so that's my issue with methodological naturalism. I believe that God is always at work all the time, and whether we pretend to shut him out or not. But yeah, I do understand soft methodological naturalism, and you have to walk into the lab looking for mechanism reasons. And that's what's so cool about science, is finding stuff.
I would say that when you cannot step outside or set aside methodological naturalism, now you've stepped into philosophical naturalism, right, in which now you've taken on the mantle of omniscience and being able to essentially state with certainty that there is nothing metaphysical outside of what I've just seen in the laboratory or the telescope.
You've also created an artificial necessity to find a natural explanation to everything that we experience.
Mm-hmm. That's right.
Going back to consciousness, for example, if you rule out anything outside of science, then you must pursue as your goal eventually a natural explanation for consciousness, which is an artificial requirement, because there are potential other explanations.
I see a current problem, though, where my problem is with, and I assume a bunch of people here are Christians, are they, I guess. Anyway, as a Christian, what bugs me more than anything is other Christians not understanding how important it is to do science and to understand the mechanisms that God has put in the universe. And they don't take time to listen to what Fuzz was saying. They would go after some other thing that, buzzes your mind or something. But that bugs me most about the church and about people who are believers. They just shut down, or they resist understanding the things that, when you understand them, you're filled with wonder, whether it's at the universe or at the way biochemistry works. Otherwise, these things would be being preached every Sunday from the sermon. It's somehow mixed in there, but you don't hear it because so many people resist it. They don't want to sit for 3 minutes to hear about DNA. And I think it's a real problem in the church that a lot of us can help alleviate by bringing these things out.
Thanks, Nick. Well, it is 10 minutes after 9 p.m. Eastern Standard Time. We're delving into our networking time, but if there are no other questions, or if there are any questions, we continue the Q&A. If there aren't, we can stop the recording for the evening and just socialize and network. Does anyone have any, what we call in the military, saved rounds? Any last minute, by the ways? All right. Well, so to formally close this evening's meeting, thank you, Fuzz, so much for being with us tonight. Again, I really loved your book. Again, just the science aside, your writing is very good.
Thank you.
So, and I appreciated all the musical analogies. So that made it a lot more fun than just educational. So Would anyone like to close us out tonight in a word of prayer? I would offer that up to anyone who would like to. All right, I will. Heavenly Father, just thank you so much for bringing everyone together tonight to fellowship and to network and to have a listening ear to hear not just what we are saying to each other, but what the Spirit is saying to us. We just thank you so much for sending your Son, Jesus Christ, to be the model for us of what it really means to be a human being divinely guided. Just again, thank you so much for the technology and the opportunity to get together in this fashion. And we just ask that your Spirit go with everyone for the rest of the week. In your Son's precious name we pray. Amen.